So, welcome to Chemistry 252. This is Organic Chemistry 2, and folks, this is your very first lecture video. Okay, so in this lecture video, think of this as an appetizer. I'm serving up an appetizer of what the rest of the semester is going to hold. And you're either going to feel very uncomfortable with the taste, and maybe you want to spit it out, or you're going to think this is the best thing ever, give me more. And I hope that's the case. I hope that you enjoy the spread that I lay out for you throughout this semester. All right, so Chemistry 252, Organic Chemistry Part 2. So before I talk about Lecture 1, which is titled Reactions of Alcohols and Ethers and Epoxides and Sulfur-Containing Compounds, I want to go back and review what you should know at this point. And the reason that I do this is because, folks, let's face it, you might not have had Chemistry 251 with me, and because of that, who knows what was discussed in your organic course. Well, here's the thing. If you took the organic course within the state of North Carolina, at any university, at any four-year college, at any community college, we have to give you the same experience, folks. We have to talk about the same exact lecture topics that everyone else talks about, because that's this whole idea of transfer equivalency. If we do not do that, we are not doing our job. So did your instructor talk about the topics that they should have talked about in a Chem 251 class? All right, so here's my chicken scratch, Chem 251, and we're going to start rattling off some lecture topics. This class typically starts off with a review of general chemistry. Did you get that? I hope that you did, because that really set up the entire semester from that point on. Lewis dot structures, formal charges, the idea of polarity, formula weights, the idea of electrons, protons, neutrons, and the structure of the atom. That is what was talked about in review of Gen Chem. Number 2, you probably, I would hope, had some type of lecture based around acid and base theory. What is the definition of an acid? A proton donor. What's the definition of a base? A proton acceptor. How do they interact? What kind of reactions go forward? How can we pick out what an acid is and what a base is? What is this whole concept of what we call a pKa value? And how does that relate to pH? All of that should have been discussed in acid-base. Number 3, after this, they finally dabbled into a little bit of organic. And that organic probably started off with the family that we called alkanes. Alkanes are really carbon single bonded to a carbon all the way down the structure. Folks, alkane structure was not the only thing that should have been presented. You should also have learned how to name these. And with this came a couple of different functional groups. Those functional groups were things like OH for alcohols, ROR for ethers, NH2s for amines. We talked quite a bit about the halogen family, the chlorine, the fluorine, the iodine, the bromine. All of those were represented. Number 4, we then moved on, and we talked about the world of alkenes, and that was a carbon double bonded to a carbon. How do we name these? If we put a group on it, some type of functional group like an OH maybe, what gets priority? How do we name those types of structures? And then in this section, we also followed this up with lecture kind of 5, and these were reactions of the alkenes. How do we break that double bond? We went reaction after reaction after reaction with that. Okay, so the double bond breaks. two sites of attachment open up, here and here. So what goes on? HBr gets added on. Water gets added on. Alcohols get added on. The list went on and on and on of what we could do. And within this category, we also brought up this term of anti-Markovnikov that I call anti-Marky Mark. And these allowed things to go on backward. More about that later on in the semester, but these are some of the things that we've discussed, or that we should have discussed, in a 251 class. Next, after the world of alkenes, folks, we went to the world of alkynes. And this was a carbon that was triple bonded to a carbon. Once more, we talked about how to name them. We talked about if they had multiple groups, how do we handle that? What if it has a triple bond and a double bond? How do we name it? If it has a triple bond and an OH group, how do we name it? Those are things that we discussed in that lecture series. Finally, or not really finally, but after the alkynes, we also talked about the reactions of the alkynes. So these were kind of two-steppers if you were going to do a dance. These two-steppers, the triple bond breaks. Two sites of attachment open up, things get added on, you're left with the double bond. And then that double bond reacts just like all the other double bonds in number 4, right? And that double bond breaks, and two more sides of attachment open up. All right, so it was just really a review of alkene reactions. That's all that was. It was just they could happen in multiple steps. After these reactions, we then ventured and dabbled a little bit into what I would call a multi-step synthesis problem. This is what we want to make. How do we get there? How many steps does it take in order to get to that product? And sometimes it would take 4 or 5 or 6 different steps. We just had to be comfortable with that. And this was also the first time that we ran across a very important reaction called a chain elongation. If we start with a compound that has 4 carbons, how do we grow it to maybe 6 or 7 or 8 carbons? Chain elongation was our friend during that time, and we used a molecule called acetylene, or the acetylide ion. And that was a C triple bond C, which is why we introduced it in that section. All right, so after the reactions of alkynes, we went back to a little bit of structure stuff, and that structure stuff is going to be stereochemistry. So in Chemistry 251, did you talk about stereochemistry? And this was the whole concept that molecules have left-handed and right-handed orientations. Just like your hand. Some of us are left-handed, some of us are right-handed, and molecules are the same way. So this kind of introduced the whole concept of R molecules and S molecules. And we also dabbled a little bit here into a polarimeter. What is the purpose of a polarimeter? What does it measure, and how does it report the data, and what types of calculations and takeaways can we kind of come up with when we do these studies? After stereochemistry, we then talked about delocalization. So delocalization was this concept that electrons move. They do not have to stay put. That means in a molecule, you have these electrons, and some of them, they're stuck. But some of them are kids on candy, if I wanted to be nice with that analogy. And they just get a sugar rush, and they go out into the front yard, and they go crazy in the subdivision. So they begin to run from house to house to house to house, and they can move wherever they want to move. And then they eventually come back home. That's okay. The parents kind of like that. Gives them some time to themselves. Well, atoms are very similar, so delocalization allows these electrons to move through a molecule as long as a certain type of circumstances exist. Some rules, some regulations. You know, you can't go out of the subdivision, you can't go out into the street, you got to be home by 8 o'clock. As long as those rules are in play and those electrons follow those rules, then they can move throughout the molecule. Finally, What we did talk about typically in the last part of a Chemistry 251 class is this whole idea of a substitution reaction and an elimination reaction. All right, so a substitution reaction came to us in two forms, SN2 and SN1, and an elimination comes to us in two forms, and that's E2 and E1. And folks, this is where we left off. Most of the time, this is where people stop. So substitution reactions, this is where carbon is a cheater. Maybe, sometimes. You know, you have really bad carbons out there, and they love to cheat. And, you know, the molecule might be okay with it. But those carbons are cheaters. They see two things at one time. Well, those are your SN2 mechanisms. They see two things at one time. Some carbons, though, kind of have some moral about them. And they're like, no, I think I need to break up with this partner that I've got first. And then when I break up with that person, then I can be single for a little bit. And then I might go out and be on the prowl for someone else. All right, so that's an SN1 reaction. So SN2 and SN1, very similar, but you're substituting. Okay, you're in a relationship, you're breaking up with that person with the intention that someone else is going to come into the picture. And SN2s allow the carbon to cheat. So one partner goes out the front door to go to work while the cheating piece comes through the back door at the same time and says, hey, carbon, I'm here. And then the SN1, that doesn't happen. Carbon says it's over, hit the curb, I'm done with you, I don't want anything else to be associated with you at all, go away, bye-bye. And that molecule leaves, or that piece of the molecule leaves, and then another substance comes in, a group, and replaces what was there. That's the definition of substitution. The elimination reactions, kind of similar, right? But elimination means you are eliminating it. That means you're getting rid of it. So carbon is in a relationship and it's just not working for carbon. And carbon looks at this relationship and says, I'm going to end it. You know, this is silly. I'm going to end this. And I'm going to say, sorry, bye-bye, you got to go. I don't need you anymore. But carbon at this point in his life or her life has decided that being single for a while is not too bad. Doesn't want anyone else in the picture. It doesn't need to rely on anyone. I mean, Miss Independent or Mr. Independent, right? That's what elimination is. So carbon cleaves the group. It doesn't want another group to come in. And these elimination reactions typically will make things like double bonds that we call alkenes. Substitutions typically just replace. That's all that they do. Now, the reason that I focused so much on substitution and elimination is because, folks, we're going to be talking about this quite a bit in reference to our very first lecture. Because substitution and elimination is typically discussed immediately before the reactions of alcohols and ethers and epoxides in sulfur-containing compounds. Whew, there's a list of awful functional groups that we're going to have to juggle. It'll be okay. Trust me, it will be okay. Something else I want to say in the substitution category. Why would you break up with somebody? Well, you know, these molecules, these atoms, it's all about what's on the outside, folks, not what's on the inside, not about personality. It's all about attractiveness. And you're going to see what I mean by that a little bit later on. But when substitution begins to happen, think of yourself in a bar. You go there with your partner. You're in there having a great time. You're laughing it up, having a few drinks. You show up with some friends, and then you look over, and there is a beautiful atom that comes in, or a handsome atom that comes in to the bar. And you look over, and you're like, oh, whoa now, wait a minute. What am I doing with this thing when I could maybe have that thing over there? And that's a substitution reaction. It's all about the attractiveness from the outside. How pretty is the group? So prettiness has a lot to do with substitution. Well, actually, this really relates to base and nucleophilicity, but prettiness, that's what I like to think about it as. I think it makes a little bit better sense when you regard it in that kind of term. Well, the reason that I'm mentioning this is because there are two groups that are super, super pretty. And these groups, I call this one Miss America or Mr. America. And that is your NH2, which is an amine. The amine groups are the best group that's out there. When the amine group walks into the bar, everybody stops whatever they're doing. It's like a celebrity. Everyone turns around and says, ho, 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 look at that NH2 group. I want that group on my molecule. Got it? Well, next in line, maybe not Mr. and Mrs. America, would be something like an OH group. And this is an alcohol. So it's not quite the best. But folks, it ranks up at the top. So if the OH group comes in, pretty much everybody at the bar stops. They take a look over at OH and they go, you're going to be my boyfriend. You're going to be my girlfriend before the night is over. That's what they do. Now, not every one of them will be attracted to OH. That's okay. Everyone has different taste, right? Molecules do as well. So the OH group is not for everybody. But the OH group is very attractive. At least it has that going for it. So what do I mean by this? What am I leading up to? I'm being sneaky here. And the reason that I'm being sneaky is because let's say that we have a molecule. And let's say that molecule is a carbon, 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 carbon with an OH group on it. And let's say that we get another nucleophile that might be swimming around in the bar or in the solution. And let's say that this nucleophile is something like, I don't know, maybe a Br minus. So the molecule looks at that Br and says, ew, you're ugly. I don't want anything to do with you. Remember, it's all about the outside appearance. Bromine is fairly ugly on the nucleophilicity chart, as well as all of the other halogens. Nobody wants the poor ugly halogens. No one does. I feel so sorry for them, but bromine and chlorine and iodine and fluorine, no one wants them. If they can get rid of them, they're going to get rid of them. They just get used over and over by these organic molecules. Poor things. Well, this molecule has an OH group. That OH group is very attractive. It's like a trophy husband or a trophy wife, right? So this molecule kind of brags and boasts a little bit in the bar, and it says, ooh, look at me, I've got an OH group and you don't. Ha 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 ha. And it looks at this bromine and it says, you're ugly, I don't want you. Look at what I'm in a relationship with. And that OH does not go away. That OH is actually not going to go away for the majority of what we call the nucleophiles that are out in the system. If you don't know what the definition of a nucleophile is, and an electrophile in an organic 2 class, I'm sorry. I'm really sorry. I'm sorry that you had that experience in 251, and maybe you took the 251 class with me, and you still don't know what an electrophile or nucleophile is, and if so, then I personally apologize to you. But a nucleophile is basically something that carries a negative charge, and it's attracted to something that's positive. All right, so here's the deal. If I look over here to the left, I'm going to see an organic molecule with an OH group. And this OH group is not complete. There's some electrons on here. That means that this piece of the molecule is polar. I see some electron distribution that is uneven. There's oxygen here. It carries some sets of electrons. There they are. That carbon doesn't have any. So electron distribution is not evenly spaced around the molecule. So this is a polar bond. Now, because the polarity is there, this is something we've got to watch out for. Because oxygen is also electronegative. All right, so the definition of electronegativity means electron greediness. Oxygen has a very high electronegativity value. As far as electronegativity value goes, fluorine is going to be the highest. And then it lowers as it goes left hand on the periodic table, and it lowers as it goes down from the periodic table. So when you find fluorine, that is the highest electronegative atom on the chart. When you go left, it gets lower, 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 lower. When you go down from that spot, it goes lower, 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 lower. So oxygen has some electronegativity associated with it. That means it's electron greedy. Think of a relationship, again, between the carbon and the oxygen is sucking all of your hard-earned money. That's electronegativity, right? You bring in the dollars, you bring in the cents, and that oxygen just takes and takes and takes and takes everything that you have made. Sooner or later, you're going to get tired of that, I hope, and you're going to put your foot down, and you're going to say, no, enough of this. But some people are okay with it because OH is pretty. Remember, it's all about the attractiveness from the outside. So this electronegativity difference, this polarity difference, allows this molecule to give us a partial positive and a partial negative charge. Well, I just told you the definition of a nucleophile is something that is negative. And it's going to look for positive things. So the bromine is going to be all by himself or herself, and they're crying all alone. And they come into the molecule and they go, oh, look, there is a carbon that's partially positive. So, hey, you want my phone number? Are you interested? And this carbon's going to look at that bromine, and it's going to look at the OH group, and it's going to go, ooh, no, go away. And bromine boo-hoo-hoos all the way off. So here's the catch. OH group, I just told you, was second in line. A lot of the other nucleophiles that we use in organic chemistry are going to be uglier than OH. But yet, we have a lecture that is reactions of alcohols. How? That's what we're going to be learning in this lecture, folks. This lecture series is going to be looking at alcohols, but it will look at ethers, epoxides, and sulfurs as well, and they all behave very similarly. But alcohols is kind of a strange one. And the reason is because alcohol is such a pretty nucleophile. If OH is on a group, if OH is on a molecule, why would that molecule get rid of it? Why would it ever look at that OH and say, no, enough is enough. You got to go. I'm tired of this. And I'm going to take that ugly bromine over you any day. Well, we can get this to happen. We can maybe knock some sense into that carbon and say, listen, buddy, it's not just all about what's on the outside. There's something more here. And you fell for the trap. You hung out with the OH for a while just because of how pretty or how handsome that OH group was. And you saw that it was kind of working, but it kind of wasn't because it took everything that you had. So why don't you try another nucleophile for a little bit? We can get that reaction to happen. And that's the purpose of this lecture series. And this all involves substitutions. So that is kind of why I stressed so much just a few minutes ago on things like SN2 and SN1, because folks, this requires a substitution, doesn't it? This OH group has got to go. That OH group makes it an alcohol. If we can make this leave and substitute it with something else, then we can get these alcohols to be reactive. we can get the alcohols to generate compounds that we might need in an organic laboratory. So, that's where this video is going to stop. That was a quick review and a little bit of insight of where this lecture is going to be heading. So sit back, buckle up. If you've had me before, this lecture probably didn't come as a surprise. And if you've never had me for an organic, welcome to my world of organic. Again, I might sound a little loopy sometimes. Maybe it's the chemicals that we have to sniff in the lab. Who knows? And at some point in time, you might feel like I have no clue what I'm talking about. Or you might question, like I always say, how on earth did he get his degree? But folks, organic shouldn't be hard. And I think that all of these silly little comparisons and analogies that I do helps you remember organic a little bit better. And if it makes me sound like a crazy person, if it makes me get embarrassed at some point in time along this semester, if you want to share these videos with friends and laugh at my expense, that's okay. I'm okay with that. Otherwise, I wouldn't be teaching this material in this way now, would I? So sit back, enjoy the show of Organic 2, and push play on the next video to learn more about these alcohol reactions.